Okay, we're talking about 10.6 in the Trig book. Other normal distributions. In other words, many sets of data can be normally distributed. And if they are normally distributed, that is the green light to go ahead and change things to z-scores. And we'll be using this formula, right? Z equals x minus mu over sigma, mu being the mean, and little sig being the standard deviation, right? Okay? You are looking for a key phrase that says approximately normally distributed, or something that just says it is normally distributed. Anytime you see that, please make sure you understand that you can go ahead and change whatever x value you have into a z-score. So, in example 1, we are starting off with a set of data about the heights of American men. And they say that the data that they collected is as an average of 70 and a standard deviation of 3. So their distribution, which is normally distributed, has most men at the height of 70, and then there's men above that and men below that, right? So it might look like this, going up in increments of 3 in each direction for each standard deviation. We would like that to be on the z-axis. So we use that formula, right? We're going to change everything to z-scores by taking the data, subtracting 70, and dividing by 3. That's going to change it to a z-score. And when we do that, our normal curve is going to look like this. We're going to have the z-axis down here with an average of 0, right? 70 minus 70 over 3 is still 0. And the increments are going to be in units. 1 unit will be a standard deviation, which matches the z-scores. So that becomes more useful to us. For instance, if you ask me for the probability that a randomly chosen male is 6 feet tall, or less than 6 feet tall, I should say, that's under 72 inches, right, when you convert that to inches. Well, since it's approximately normally distributed, we can change it to a z-score. 72 minus 70 over 3. That's 2 on the top and 3 on the bottom. So in other words, this is the equivalent of the z-score formula over here that you see. The probability that x is less than 72 is the same as the probability of z being less than 2/3. These things are equal. Now I know how to calculate the probability that z is less than 2/3. I'm going to use the normal CDF function on my graphing calculator. Alright, now keep in mind, right? Zero's here. 2/3 is here. We're looking for everything to the left of that. So I know that 2/3 is the right boundary, but what's going to be my left boundary? Something smaller than -3. I am going to pick -10, as I always do. So you get out that calculator. Let's figure this out. Second distribution button, right above the vars button. Normal CDF, cumulative distribution function. We've got a left boundary of -10 and a right boundary of 2/3, and yes, you can enter a fraction. 0.748. So almost 75% of all the men, American males, are under 6 feet tall. Okay, example 2. I'm going to have to read this one out of the book because it's a little bit detailed. It says that refills of a, let me grab the microphone a little bit here. Refills of a particular mechanical pencil are supposed to be 0.5 millimeters in diameter. When they say it's supposed to be, that's your average. That's the target. That's the perfect value. Refills that are 0.485 millimeters or less in diameter do not stay in the pencil. In other words, they fall out and they're no good to us. So we have to throw them away or grind them up and reuse them. While those that are 0.520 millimeters or more do not fit in the pencil at all. So once again, you're going to have to grind them up and redo them. If a firm makes refills with diameters whose differences from the correct size are normally distributed, okay, there's my key phrase, normally distributed, with a standard deviation of 0.01. So right now, I know that the target value for these diameters is 0.5, and they're telling me that it's got a standard deviation of 0.01. It says find the probability that the randomly chosen refill will fit. In other words, it's got to be between 0.485 and 0.520. Now, because we saw the phrase normally distributed, that is our green light to go ahead and change it to z-scores. Okay, so let me grab my calculator here. And we have 0.485 minus, oops, not times, minus the average divided by 0.01. So negative 1.5 is my lower z-score. And then 0.520 minus 0.5 divided by 0.01. So we have 2 for the high side. So my z-scores are negative 1.5 and 2. So keep that in mind. This is based on the X scale. This is based on the Z scale, for which we're going to use our graphing calculator. So we've got our normal CDF function now. We're going to second distribute normal CDF. And we already have our left bound and our right bound, so we just type those values in. Negative 1.5, comma, 2. 0.91, we'll just go with 0.91. So 91% of the value of, so we're 9% of our of the product that we are producing has to be reused, reground up, and made over again. Hopefully, it's not a product that we will lose 9% of, but we'll just have to reuse. And then maybe the company has to go through a process of figuring out, okay, what can we do to get that number, that percentage down, so that we are manufacturing good pencil leads the very first time that we actually produce them. Okay, now I'm going to show you a picture from the book. The binomial distribution, which I know we're familiar with, the whole success and failure thing that we talked about toward the beginning of this chapter. We have a fixed number of trials. So we would make histograms. That's what we did in section 10.1. And if you get a lot of trials, then you can get what looks like almost a normal single-peaked bell-shaped curve. Well, that's going to look an awful lot like a normal curve eventually, right? I mean, you're going to be making more and more and more and more of those little tiny bars, right? Not the gold variety. All right, although that would be nice if we could find those, right? Because then we could retire. Yeah, you can write that one down too, Schneider. So, but all these little tiny bars are going to fit perfectly or close to perfectly. I should say close to because it won't be exact. As you can see, even in this picture, some of these little boxes go outside and some of them do not fit underneath perfectly. So here's the whole deal. We can, if we have enough trials, we can approximate, or I should say, if we have enough trials, can a binomial distribution be approximated with a normal distribution? And the definite answer is yes. Okay, so what's the condition? When can we do that? Well, here's the condition. If NP is greater than or equal to 5 and NQ is greater than or equal to 5, yes, that's the number of trials times the probability of success and the number of trials times the probability of failure. If those two things are true, then we can change it to z-scores. In other words, normally the binomial situation means I have to use the binomial PDF, probability distribution function, and I have to find individual probabilities for all those little bars and then add them up. Well, if you get enough trials, that's going to be a real pain in the behind. So it would be really nice if we could convert it to z-scores and just use the normal CDF function and get this thing over. So let's look at an example like example 3, which is binomial from the very beginning. All right? And I'm going to have to read this one as well. So let me grab the microphone here. In the past, about 85% of ticketed passengers have shown up for regularly scheduled Chicago to New York flights with a capacity of 240 people. So in other words, it's a binomial situation because we have 240 trials, or a fixed number of trials, depending on the number of tickets sold, and they either show up or they don't show up for the flight, for which I have no idea why you wouldn't show up for a flight unless you were changing your ticket or something. The airline company proposes to accept 270 reservations. In other words, they accept 270 reservations, and then they have, if they go over, then they put people on different flights or upgrade them on, in the future, give them extra tickets or something like that. And then obviously there are several situations where enough people don't show up, so they have plenty of seats, or the 270 turn out to be 240, and they still have a full flight, which is making the airline company the money that they want. So here's the question. What's the probability that with this policy, the Chicago-New York flight will be overbooked? Okay, what's the probability that they will be overbooked? Okay, hold on a second. All right, so we know that the probability of success, or a probability of somebody showing up, is 0.85, and the probability that they won't show up is 0.15. And we have 270 tickets or reservations that we have for this particular flight. So we need to do our check, NP, NQ. So let's see here. 270 times 0.85. That's 229.5. 270 times 0.15. 40.5. Both of those are greater than or equal to 5. So now we know that we can change this, because they want to know what's the probability that we will have more than 240 passengers. And do we really want to do this? Do we really want to use the binomial probability function and calculate the probability of 241 passengers and 242 passengers and 243 passengers, all the way up through 270 passengers, like everybody showed up. I do not want to do that. So, since this is true, we just figured that out, then we can approximate the above equation using the z-score formula, right? Subtracting the average, okay, what's the average? Oh, that's right, that's NP. And we just figured it out. That's 229.5. That's right, that's N times P. What's the standard deviation? Oh, that's the square root of NPQ. We haven't figured that out yet, have we? Okay, well, maybe I better back up. Maybe I better figure that one out. I've got NP, right? That's 229.5 here. I'll get a space up here. Square root NPQ. That's sigma, right? NP, we know that's 229.5. We know the probability of failure is 0.15. So let's just calculate this part. 9.5 times 0.15, and let's take the square root of that answer. 5.87. 5.87. So back here on that screen, when we were trying to figure that out, that would be 5.87. So they did not hand me the mean and the standard deviation. I had to calculate those based upon what we did in section 10.2. So if I want to know what's the probability that more than 240 passengers are going to show up, I'm going to change that to a z-score by subtracting 229.5 and dividing by 5.87. So this is the probability. Oh yeah, I asked those questions down here, but we just calculated them, right? Remember NP and square root NPQ. That's the probability that Z is greater than, drum roll please, excuse me. Please and thank you, yeah, you know. So we subtract those, right? We divide by 5.87. We get a z-score of 1.79. 1.79. So let's think about that. We've got 0 here, 1.79's out here. We want bigger than that, so we're talking about this area under the curve out this way. So, with that being said, oops, not that far. We want normal CDF 1.79 would be my left boundary. What would be my right boundary? Something bigger than 3. I always choose 10, although it just has to be bigger than 3, really. Whoops, too far. Second, distribution, normal CDF, 1.79, comma, 10, comma, parenthesis. There is a 3.7% chance. 0.037. So, that's what they have to be prepared for in order to, give away those extra tickets or upgrade passengers or whatever they need to do in order to fill the airplanes and make sure all their customers are happy. They need to be ready for 3.7% of the time to have more than 240 passengers. So, if that's an acceptable amount, then they should keep doing what they're doing. Otherwise, they should lower the number of reservations. But the key point that I want to make to this particular example is make sure you understand that just because it's a binomial situation in the beginning does not mean that you can't use the normal distribution. Use the test to check And if it does work out, then use the normal distribution. Change it to z-scores. Okay? Now, if they tell me from the beginning of the problem that it's normally distributed, do not hesitate at all. Change them to z-scores. Okay? We need them to be z-scores if it says they're normally distributed. And if it's a binomial situation, check to see if it works out. Hey, if it's binomial and it does not fit the test, if NP and NQ are not both greater than or equal to 5, you better stick to the good old binomial, PDF function that's in your calculator that we talked about before. So make sure you remember that as well. Talk to you in class.